Welcome all to my second lecture. In this lecture, we will try to talk about a header files provided by the chip manufacturer. So we will take one of the header file provided by Texas Instrument. We will try to understand what is the meaning of the header file. So for any problem, first your fundamentals should be strong, or you should try to understand the fundamentals. So that is the motivation for this lecture, because for any of the microcontrollers, if you take Microchip, Infineon, Texas Instrument, any microcontrollers, normally the header files will be provided by the OEMs, and we'll just take it for granted. So we should try to understand what is the meaning of the header file. Let's jump into the video. The topic today, what we cover is the general block diagram representation of the microcontroller, peripheral header file provided by an OEM. So normally we had seen the peripheral header files of different peripherals like GPIO, ADC, PWM, CAN. The header files will be provided by the OEM. So we will try to take GPIO. We'll try to understand some very important information which will be very exciting and very useful. And then we will also talk about the significance of memory location of the peripherals. So there will be some start location, there will be some offset. So we will look into the memory locations, and also we will see the GPIO registers, how does it has to be finally distributed in the memory. So let's get into the video. So general block diagram representation of microcontroller. So if you see, there will be a CPU, a central processing unit, flash, which is a non-volatile memory, which means if the power goes, still the data in the flash will be still exist there. Which means if I try to write, say, some const x is equal to some 10, even if you switch off and switch on, we can see the value will be still present in the flash. So we will see in detail the different sections of the code and other things in the subsequent lectures. RAM is a volatile memory. So the data, whatever we write, once you switch off the power, the data will goes off. Then you have different peripherals, GPIO, PWM, and ADC. So again, you have many other peripherals, but I really don't want to show a lot of things. So I would just want to keep it simple. So to understand CPU, if you want to do, let's assume that if you want to do z is equal to x plus y. So maybe x will be taken from flash or RAM. Y is another variable which will be taken from the RAM. The actual calculation will be executed in the central processing unit, the CPU, that is z is equal to x plus y. And maybe that result set has to be written to some register which is sitting in a defined memory space. So if you see the GPIO peripheral registers or the PWM peripheral registers, ADC, they have a defined memory space dedicated for the registers. You cannot use these memory locations for any other purpose. Like for example, let's assume that you want to write some x or y or some variable. You cannot put into a memory location which is defined for the peripherals. So right side is what the same block diagram representation I took from the datasheet. So dual C2A CPU is lockstep. Okay, lockstep is some feature where the same function can be executed in two different places. FPU32, so it's a floating processor unit. TMU, it's a trigonometric unit. VCR, CCRC. So this is also a like cyclic redundancy check. So these units are some inbuilt hardware units which basically helps to run some instruction at a very quick rate inside the CPU itself. CPU timer, uh, it's a peripheral. PIE, it's an also a peripheral. Crystal oscillator, we have the either an internal crystal or internal RC oscillator or external crystal, different options you have. And then you have, as we have seen, the simple block diagram, you had dedicated flash as well as a RAM. Normally, if you see the size of the microcontroller, typically the flash memory will be of higher size, whereas the RAM size will be lower. The reason behind this is when you compile the code, the whole different functions will get converted to dot text, and everything has to be saved somewhere. So that's the reason why if you see typically the memory of flash, so that's you can see this, it's around 256 KB, whereas the RAM M0, LS0, so there are different types of RAM. Uh, so this is 4 KB and another is 32 KB. So this is what the general topics or the RAM and flash what we have in the device. Then you have all other peripherals, PWM, input output X bar, SCI, 12-bit ADC and things like that. So now let's try to get into the interesting part of the lecture, the registers in the GPIO. So this data sheet, or let's go to the data sheet quickly. Okay, so if you see the data sheet, every peripheral, if you see at the end, if you expand or you just open it, you can see there is GPIO registers. If you see crossbar, you can see some registers. ADC, you can see some ADC registers. So where the registers, the detailed information about each and every bit will be explained. So now let's quickly go to the GPIO registers. So here we can see of this particular device 15X TMS 320F280015X. There are three different structure. High level, if you see, there are three different structure. One is the GPIO control rex, GPIO data rex, and then GPIO data read rex. And the base location is given. So 7C00 is the start location of the control rex. Data rec consists from 7F00 and data read rec starts from 7F80. This memory is defined only, or it is stored, or it is reserved for this particular peripheral itself. Okay. So now let's take the data sheet as well. So we can take both like both sides. Okay. So I took the data sheet, or the data sheet I have on the right side. The left side, I have the header file provided by the Texas Instrument. We have discussed in the last lecture. Once you install the control suite, you can see this path CTI C2000 device support headers include, and GPA.h file. Correct. So now let's get into the topic. So you have the starting, what we can see is GPACTRL. So what does this GPACTRL means? If you try to go, then we can see this defines the sampling period, for how much time a GPIO has to be sampled. So the first 4 bits, qualification 31 to, or let's start maybe from LSB 0 to 7. So the first 8 bits define the sampling period for GPIO 0 to GPIO 7. So you can choose like 0 to 7. So you can choose any value from 00 to 0FF. So FF is the maximum. So this defines the sampling period of all the lower 8 GPUs, which means you cannot have a different sampling period for individual GPUs. So this is 8-bit, again qualification period 1. This is for GPU 8 to 15. So it's qualification period 1. then period 2, which is for 16 to 23, and 24 to 31. So it is totally 32 bits. So you can see each bit is of 8 bit. So the element in each of the in this particular structure called as GPA CTRL bits, each is of 8 bit and total size is 32 bit. Now, rather than writing individually the bits, like let's assume that you don't want to update only the qualification of some GPUs. You want to write the qualification of the entire GPUs starting from GPU 0 to 31. Then what we need is some union, because both it should share the same memory location as we have explained in the previous lecture. So that is the reason why they are used the union. So the union name is nothing but GPA CTRL rec. So some common naming convention TI is using. So that is nothing but GPA CTRL underscore rec. Now let's again go to the next register. So that is nothing but GPA Q cell 1. So let's right side, we can go to the section. So this defines the number of samples for which we have to do the qualification. Okay. So again, this is, if you see, there are 4 different modes. So that is the reason why you need 2 bits. So it starts with GPU 0, 0, 1. Then like if you have all 32 bit means you can have only up to GPU 16. Then again you will have something called GPS L2. So GPS L2 basically conveys from 16 to 31. So now if you try to see here the structure definition, again you have something called GPA Q cell 1, which each is of 2 bits, GPU 0 to GPU 15. Again, if you want to update for all the GPUs right from GPU 0 to 15, then you need union. Then we have something called GPA Q cell 2. What we can see here, it starts with 16 and then it goes up to all the way up to 31, right? So now if you try to go to the next thing, that is nothing but GPA Mux 1. So GPA Mux 1 defines you the mux selection. So one particular GPU can be used for multiple purpose depending on the pin configuration. So maybe that particular pin can be used as a PWM, UART, GPIO, CAN, different options. So this is the bits what you want to write so that you can configure the usage of the GPU. So you can see the GPA mux where the each is of 2 bits, right? So now let's try to understand. So it goes on, right? So if you see the 7C00 is a start location, then even though the registers, what we had seen was, for example, the starting at the qualification period, which is of 32 bit, but the way how it is stored in the memory is of 16 bit, 16 bit. So that is the reason why you can see it starts with 7C00. Then the next register, it basically goes to 7C02. So there is an offset of 2 bytes of data. Okay. So yeah, to verify this, we can just go to the data sheet again. So yeah, we can see the GPU registers. Yeah. So you can exactly see it start with GPS CTRL, which is of 16 bit, but 32 bit. The registry is 32 bit, but it is split into 2. So 7C00 consists of qualification period 0 to period 0 and period 1. Then 7C01 for period 2 and period 3. So that is the reason why you can see the GPAQ cell 1. Again, it's 32 bit. So it starts with an offset of 2H and then it goes on. So GPAQ cell 1. So again, it's 4 bits. So and then it goes on. So again, we can see here. So I try to show you the whole example, not the entire register, but at least I tried to show how does the offset goes on for each and every registers. So you can go through the data sheet and along with the memory or like the distribution, which will really help. And also you can see something very interesting is the reserved type 7C0E. So like let's maybe again take the data sheet once again. So if you see, let's yeah, so 7C0D. So we reached GPA. Yeah, you see this PD. So there is something called C, right? So we are also having C, and then C and D. So yeah, which I conveyed to 16-bit. So C 700D. So after D, we are not having E and F. It directly jumps to the next location. 10. So there is no two. The two memory locations are like it is not used for some purpose for this data sheet. So then what we need is we need some uh, like we cannot use these locations, right? So how to handle this, that is, that will be very interesting. So basically the some dummy location will be given. So let's maybe quickly go to the GPA, try to find the uh, GPA pull down GPA PUD. Yeah, so yeah, you can see here. So the 16-bit, right? The 16-bit, which is of two arrays. So basically, the two memory locations are reserved. Correct. So like this, we can see the GPO control registers, the different registers. Like yeah, the unions are defined above and an instance is created. And these all are a part of the main structure called GPIO underscore CTRL underscore rex. So you can see all the registers, whatever which is defined in the data sheet under the heading GPO CTRL register, you can see everything will be there till the GPHCR. Correct. Then it will go to the next uh, uh, next, which is nothing but GPA data register. So if you try to expand this, if you try to go to the GPO registers, and then if you try to go to data registers, then yeah, again you can see it again starts with GPA dat, which is basically a single bit to to write it as high or low, like things like this. So GPA set, and then it goes on. So again, you can see the corresponding structure, what they have defined here. And then finally, what you have is your the the read registers, right? So you can see the read registers also, which is given at the end of the. So again, the whole union in the data register, you have multiple other elements, which is a part of the whole structure. So that is the reason why it is all clubbed together. And then finally, you have something called your data read regs. And then we have, so like the structure tag name is there, we are creating an instance. But please note, this is an external. We are saying that the definition is defined somewhere. We will see where it is defined. But yeah, this is an external volatile struct, which means it's a structure which is a volatile, which can change. And then we are also saying that it is external, means there is somewhere the function has to be defined. Unless otherwise you define it, it will not have any memory location. Correct? So I hope you have some good insights or some good understanding on how does, like, what does this header file means. Now let's try to talk about actually what is peripheral header file. So as I've conveyed in the lectures, you should try to ask yourself, like why and why. So basically this header file is a high level C language interface document which helps map the peripheral registers in the defined address space. So let's assume you want to control a GPIO1 as an output. Let's assume that you want to control some GPIO1 as an output. Then you want to write something in some memory locations. So to do this, basically we are, or the OEM is providing you this. Uh, OEM can provide, you yourself can write. It's not something like something big. Uh, so, but what you want to understand is this is just a high level. We cannot, rather than putting something to the memory location, basically this is a high level C language interface document. I will call like this, uh, which is helping to map the peripheral registers in a particular address location. So if you see, to use this, you want to define as an output, and GPA as well as GPG mux1 will be there. So the second and third bit, uh, because 0 and 1 is for GPS 0, 1 is for, so at this particular memory location 7C06 and at 7C20, you need all bits to be 0. And to make it as output, the first bit of 7C0A, so 7C0A is nothing but your GPA direction. You want to make it as an output, and that bit should be high. So if you really are interested, then you can, once you use this structure, and then if you go to the disassembly code, and then if you try to see this memory location, you can see these values. So this value will get updated once you automatically write that value to the structure. It will be very, like very interesting. In the coming lecture, I will try to show you how does, how does it finally goes to a memory. So the header file provides a C language structure for writing the required value in the defined address space. So that's the conclusion of this particular video. Hope you have some insights, and I hope this time what you spend for seeing my lecture was useful. So if you are again excited to see my next lecture, please go to the next lecture. I will also give in my first comment section the previous videos. Thank you.